So I'd like to do another example where we get the potential and then the E field. The problem is a sphere. It's a shell. It has uniform charge density sigma. It has a radius r. And so what we'd like to do is find the potential both inside and outside of this shell. We orient the sphere so the field point is along the z-axis. I'll be using z. Realize that we could have used little r for this vector here, but we'll just use the parameter z. So we'll take the origin at the center of the sphere. We'll let the source point be this little patch of area. We'll call it ds prime, so that dq is sigma times ds prime because this is a constant. We're going to be using our surface area version of the potential, and so we'll have to find r prime, and then the magnitude of r and r prime, and we'll have to define ds prime. So here's my translation. Our r vector is along the z-axis, so it's in the z-hat direction, and we positioned it at a distance z from the origin. Our r prime is on the sphere, so it's a distance r, and will be in the direction of r prime. And so I've tried to show it here where this is sort of towards us. So this is the vector r prime if we were to put an arrowhead on it. The dq is equal to sigma ds prime, and ds prime for a sphere with constant radius r. You square the r, take the sine of theta prime, d theta prime, d phi prime. Here's theta prime with respect to the z-axis, theta prime from z to r prime. Phi is just the angle in this direction here. We're not going to have any dependence on phi, so that'll make it easy to integrate. Here's our r minus r prime. It'll be the z vector, z hat. This is r, and then this is r prime right here. So minus r hat. If we take the magnitude of this, we first form the square. We take r minus r prime, which is right here, we dot it into itself, and that will be the length of the vector squared. If we look at this, we'll have z dotted into this dotted into this, and then we'll have the cross terms. The cross terms are identical, so we end up with a 2. Then the minus sign comes from the fact that we'll get minuses from these minuses here. So here's our r squared, that's this term dotted into this one. Here's our z squared, it's this term dotted into this one, and then here's the remainder, which will have an r, a z, and then z dot r prime hat. But what is that? Well, take a look at your picture here, and what you find is the unit vector between the z hat vector and the r hat vector. Those two vectors are separated by this angle theta prime. Well, if you remember the dot product, it's equal to the length of the unit vector, the length of the unit vector, times the cosine of the angle between them. So we can rewrite the distance between these two vector ends as equaling this quantity here, which is this quantity right here with cosine theta substituted in for this, all to the 1/2 power. So repeating, here's our translation, here's our dq, and here's our integral. So we're going to use dq as sigma ds prime. Notice that you have this set of factors here which will show up. What we're doing is building this integral. First of all, k sigma. Sigma is constant, so that can come out. ds prime would be equal to this quantity right here. This is ds prime, all of this. ds prime would give us a d phi prime, a sine of theta prime, and a d theta prime, and the r squared. Okay, let me repeat that. Here's r squared, r squared. Here's our d phi prime right here. Here's our d theta prime here, and here's our sine theta prime here. So I want to account for all the factors in dq. That's divided by this quantity here, and so that's what you see here, the r squared, z squared, minus 2 times this, all to the 1/2 power. The d phi prime integral is just 2 pi, so that's this factor here, so we rewrite it, and then here's our theta integral all isolated by itself. Okay, so here it sits, and we want to evaluate that. And so the first thing I want to tell you is that we have to treat inside outside separately. It won't be obvious because we're going to use Mathematica for this, and I've made that assumption right here. If you did it by brute force without taking into account the relative sizes, you would end up with some square roots that, if you weren't careful, could go imaginary. And so you have to use two different methods to get the outside and inside answers. So I'm saving you this trouble by just telling Mathematica, find me the integral for z outside, and that's what this is right here. This is the answer. It comes out, by the way, in terms of an absolute value. Our absolute value is just the same as the argument because these are both positive. This is just equal to the argument. So that's what this is right here. Then we add r minus z. Take that sum, and so you get 2r plus 0 divided by r over z. The r's cancel, and so you're left with 2 over z. So that'll be useful. Okay, now let's do the other case where we have z less than r, same integral, and it comes up again with an absolute value of r plus s. But now we have minus r plus s. This one was plus r minus z, z, minus r plus z. So work that out. This is again just the argument itself, and so put that out here. I've changed the order. We end up with 2 because we get 2z, and this will give us 0. So we get 2z over rz, and that's 2 over r. So you can see they're quite different in terms of the results. And I repeat, you could have done this brute force, but you would have had some square roots to interpret. One would give you this answer for this condition, the other would give you this answer for this condition. Mathematica was able to do them both if we put in assumptions that I show you here. Now we can write the total package here. There's this prefactor, which is right here. This is the prefactor, times the integral. And so if we're outside, it's 2 over z. Simplify that a little bit. Use the fact that k is 1 over 4 pi epsilon naught. This will be your potential outside. And it has 1 over z, which is interesting because it's looking something like a point charge. Inside, you go through the same steps. You have the prefactor and the integral. Simplify that, and it's sigma r over epsilon naught, which is a constant. So inside, the potential is constant. Outside, it depends on z. So here's what it looks like. Here's our constant value here, and then as soon as you hit the shell, then it falls off with 1 over z. If v is a constant, if we take the gradient, we'll get 0. So inside, you have 0 electric field. Outside, here it is again. If you notice back here, we could have put 4 pi r squared in front of the k sigma. If we do that, it looks like this. So here's our 4 pi r squared. That's the area of the sphere. Area times sigma gives us q, and so we have kq over z, and it is in fact the potential of a point charge. Well, let me just interpret that a little bit. If you apply Gauss's law to this surface charge, what you would say would be that because of the spherical symmetry, the E at any point must be a function of r only, and should be in the r hat direction for both inside and out because of the symmetry. If you have this kind of symmetry, then you can take spheres for Gaussian surfaces. So here's inside, and then of course you have another one outside. Inside, because of this condition here, and the surface vectors being parallel r hat, you'll end up then with the integral factoring out the E field along this surface. That results then in the left-hand side giving you the magnitude of the field. But the right-hand side, there's no charge inside, so the Q enclosed is 0. So you conclude then that inside, for any r inside, the field is 0, which is what you should get for this constant potential. Outside, you can again argue the magnitude of the E field should be related to just the charge inside, and that has to do again with symmetry. So when you make that conclusion, the charge inside is Q, where Q is equal to sigma 4 pi r squared. So you would conclude then, outside, you would get this expression, and you would conclude that because of this symmetry, the field outside is equivalent to all the charge being put at the center, and you get the field of a point charge if you're outside. Starting from scratch, which was this integral here, for both inside and outside, we're able to get the full description of the electric field by using our gradient equations in order to derive those. If we have a choice, we might want to use this because of lack of symmetry. When you have symmetry, it makes it a little bit easier. Very high symmetry, Gauss's law, gets you that E field. Now there are times where you really want the potential for looking at the way particles would be accelerated, for example, because your energy is related to the potential. There are other reasons for wanting the potential as a function of position. The bottom line is that if you have this, you can find E. Sometimes this is the only way to get the E field because you can't do it directly.